Hi friends, welcome on board for another project. This time I decided to design this board for you. It is actually based on RP2040 microcontroller. Do you see the board? It is connected to this sensor using an I2C interface. This sensor is INA219. It is a digital current measurement sensor. It reads the voltage and current values digitally and sends the data to the microcontroller. So we have the voltage and current, we can calculate the power as well. So the microcontroller shows the data on this 3.2-inch TFT display. I have designed this graphical user interface myself. All of the values are 0 except for the voltage, and it shows this value because the sensor is not connected to anywhere. It's floating, so it shows some wrong value. Otherwise, if the ground connection of the sensor is correct, it's not floating, then this value would be 0 also. Later on in the testing section, I will connect the load and test the board using my DC load. But at the moment, let me explain the board just briefly. But before that, let me mention that you can download all of the project data or the project files from my personal Altium 365 cloud space. So first, you should register on the Altium 365 website. So simply follow this link and register on the Altium 365. Then follow this link and download the project files for free. Let me explain the board just briefly, because in the next step I will explain the board live on the cloud. So this is the board RP2040, the input, either this USB Type-C or this XH, linear regulator, and this side, I should be careful for this flat. These are the necessary resistors to run this TFT display. I will explain on the schematic, and the back side is almost a solid ground plane to stabilize and the circuit and reduce the noise. For the sensor, okay, this is actually for prototyping. In the real world, you should design your board and just connect these wires to your board. Otherwise, I don't like the PCB design of this module, but it works for prototyping. It's okay. But as I said, if you want to use this design seriously, you should design your board, final board, using this sensor and just connect the wires from your board and this controller. Alright, let's go to the schematic and PCB. Alright, here is the home page of my Altium 365 cloud space. If I show you the menu, I have created this my Vanitar space, and I have uploaded all of these 8 projects so far. The rest belong to the Altium itself. You can use them as a sample. Of course, you can create your own space for free, the same as me. Just follow this link in my YouTube video description and register on the Altium 365 website. Then come here and upload your projects and share them with your friends or your colleagues. But you may ask, what's the main benefit of this Altium 365? Why I should register? The main benefit of this Altium 365 is when you're working on a project, especially if this project is complex. And definitely, the team members will apply some edits and will mention some feedbacks. For example, they will tell you to change this resistor value, remove that track, add that differential pair, or whatever. Without this Altium 365, you have to exchange many emails and you will live in a mess of emails and PCB files. But here, when a team member applies an edit or mention a comment on whatever, all of the team members will get that update instantly live on the cloud. So all of you are connected on one PCB project, and all of you will receive that update instantly, and you can communicate. This was the main benefit. Of course, it has many features, but you will get and you will notice those features when you register on the website. By the way, here is the latest project, the schematic document. This one is the PCB layout, and this one is a 3D view of the PCB board. Let me explain the schematic. This one is the RP2040 Zero board. Here is the input supply, 5 volts external. These two capacitors are decoupling for noise reduction. Why I put this Schottky diode? Because you have to separate the supply of the USB when you program your board and the external supply, because you might want to program your board when the supply is connected. So this Schottky is mandatory. Here is the USB Type-C connector. For some reason it does not show the logo of the USB, because this is the original document, schematic document, and both of these components show the logo. Maybe here I should also upload the images, because it says cannot open this, and I should change the address to point to Altium 365. Anyway, it doesn't make a difference. As I said, USB Type-C, and these two resistors are to indicate that this is the load side, and for high current, the current consumption of this circuit is low, around 120 milliamps, so you can forget these two resistors, because these two resistors are to get higher current than, I think, 500 milliamps. So anyway, it's a good rule of thumb if you want to solder these two resistors. This is the current sensing module. As I said, the protocol is I2C. These two capacitors are decoupling for noise reduction. This is the TFT display, 320, 240, 3.2-inch. I have configured the display to get the data through SPI, and these three resistors define the protocol, either parallel through these pins or SPI. And when I use SPI, you have to connect all of these parallel pins to ground. The backlight of the LCD uses 3.3, so you don't need to use a boost converter to drive the backlight. However, I have also added this R4 4.7 ohm resistor to limit the current to the backlight, because the maximum brightness is not necessary. It's okay with a little bit. 100% backlight is not necessary. These two capacitors decoupling for noise reduction and stabilization of this TFT display. And this is a 3.3 regulator to supply the current sensing module and also the LCD, because the RP2040 gets the 5 volts input directly from the USB or this one, the XH connector. Let's go to the PCB. Here is the PCB layout, 2 layers, the top layer, bottom layer. If I disable the top overlay, this is the bottom layer, almost a solid ground plane to reduce the length and impedance of the ground path. Let's go to the top. You might say, what's the problem of this DRC error? Actually, it's not important, because the schematic or the PCB does not know that these two pins are connected internally inside this chip. So it shows this DRC error to indicate that this pin left floating. It doesn't matter, it's okay. I have also added these wires to reduce the length and impedance of the ground path. Directly they are connected to the bottom ground layer. The PCB is simple, nothing very much to talk, but here the frequency of the SPI here is around 40 megahertz. You might say that it is better that we use differential pair, but it's not necessary because 40 megahertz is not that much high, and also the tracks are short, so it does not make any issue. As you will see in the next step, the LCD works okay. But if you use differential pairs and I mean length matching, if you use length matching, it's not bad, but it's not mandatory, it's not necessary. Okay, I think I covered most of the points, nothing very much. The 3D view. This is the LED that blinks. I have added this one to show that the microcontroller works correctly, because I have used both cores of the microcontroller. It's a dual core microcontroller, and this LED to show that the input power is at the correct level. The FPC connector, 40 pins, and pretty much that's it. Let's go and test the board. Alright, I have prepared this test setup to compare the results of our circuit, voltage, current, and power with this commercial Siglent SDL1020 DC load, voltage, current, and power. However, I don't expect these two devices match each other because my setup is not good, the PCB of the module is not good, the power rating of the shunt resistor is only 1 watt, it will warm up in high currents and will introduce some tolerance. Anyway, it gives us a picture, because if you design a good PCB for the current sense part, you can expect very good results, because it's a 12 bits current sensing IC. Let's apply some current, for example 45 milliamps or 450, anyway 450. Let's go 45 milliamps now. 45, it has only 2 digits after the points, so it shows only 4. Let's go to 1.23 and apply 1.23, 2.5. Now I expect some tolerance. Yeah, you see, because the current is high, it warms up the shunt resistor and introduces this tolerance. But if I go down, for example 85 was, because 85.5, 86, okay. That's why I said use a good PCB. But okay, it gives us a picture, and so far the results are pretty good. Just follow this. You have a good graphical user interface, design a panel for your device and put LCD here and have fun. Give me a big thumbs up. We will do something else in the next video.